Welcome to homework.
In this problem, we got a harmonic oscillator, quantum harmonic oscillator. We are going from the n equals 1 level to the n equals 2 level with a photon of 6.5 micrometers. That photon is absorbed. Its energy is able to bump this up from the n1 to the n2 energy level. And from that, we should be able to figure out what photon wavelength would be required to go from 2 to 3 energy level and from 1 to 3 energy level. And then finally, what's the classical root k over m for this oscillator? So to start, the only equations we're really going to need for this are the energy levels equation for a harmonic oscillator, which goes E sub n is n plus 1/2 times h bar root k over m. And then we also need to know that the energy of a photon is related to its wavelength by hc over lambda. So with that information alone, we should be able to get everything. So starting off, we're going from n equals 1 to n equals 2 energy level. And that energy difference will be equal to whatever the energy of the photon that was absorbed is. So E sub p, E photon is equal to the change in energy, delta E, which in this case is E2 minus E1. Plugging that into the energy levels equation, we are going to end up with 5/2, I believe. Well, actually, let's 5/2 minus minus 3/2. Multiplied by our h bar root k over m, which of course we will end up with h bar root k over m. And the interesting thing about a quantum harmonic oscillator is that each energy step is this. They're the same steps going from any energy level to any adjacent energy level. So because we're going from 1 to 2, we now know what the adjacent energy step is. So this result right here, h bar root k over m, that's going to be our result for any adjacent step. So we would set that equal to hc over lambda, which is the energy of the photon, which would come out to be about 0.19 eV once we plug everything in and convert to eV. So this is going to be the same for the going from 2 to 3. It's going to be the exact same energy because any adjacent energy level is going to be the same amount, which is this 0.19 eV. And to go from 1 to 3 is going to be double this because it's two adjacent steps. So it'd be 0.38 eV. So now the last thing we're really asked to do is find this root k over m. Oh, well, actually before that, we need to find the wavelength to go from 2 to 3 and 1 to 3. We know the energies are we know what the energies are. We just need to do one extra step. So for lambda 2 to 3, it'll be identical. It's the same lambda as lambda 1 to 2. And for 1 to 3, we need to do 2 delta E 1, 2 equals hc over lambda. Thus, lambda is hc2 over the energy gap from 1 to 2, which would give us about 3.25 micrometer. So we'll need half the wavelength to do that full step, which is reasonable. And now we can get to the final step to find root k over m. So we can start with, if we know what this step is, delta E sub 1, 2, we know that we found that was equal to h bar k over m, and we know what its value is. Thus, root k over m, isolating it on its own, is just the energy difference over h bar, which will come out to be 2.9 times 10 to the 14. And I'm not sure exactly what those units are. Oh, actually, if it's equal to delta E over h bar, it's joules over joule seconds, so inverse seconds. Anyway, that's its value. And I think that's everything we were asked to solve.